Let's look at how the atomic structure of aluminium provides its engineering properties. The atomic number of aluminium is 13. Aluminium has 3 electrons in its outer shell, which contribute to its free electron gas. This leads to excellent electrical conductivity. Aluminium atoms form a crystal lattice with a face-centered cubic, FCC structure, allowing for high packing efficiency of atoms. Aluminium crystals can change shape through plastic deformation, which occurs by the slip of atoms when sufficient force is applied. Slip primarily occurs on 1-1-1 planes, facilitated by the movement of dislocations, which are boundaries of extra planes of atoms. This localized slip requires less energy. In commercial applications, aluminium usually contains impurities like iron and silicon. These impurities lead to the formation of insoluble particles, impacting material properties. Alloying elements like copper and magnesium dissolve in aluminium, distorting the lattice and influencing its responses to mechanical and thermal treatments. In a solid solution, the foreign atom substitutes for an aluminium atom. These foreign atoms are known as solute atoms. They have atom sizes that are different from the atom size of aluminium. This means that solute atoms introduce a distortion into the aluminium lattice. It is a feature that has a controlling influence on how the alloy responds to heat treatment and to mechanical working. As the liquid aluminium cools to, and then below, the freezing point, small crystals of solid start to grow within the liquid. The solid crystal grows at different rates in different lattice directions, and the crystal takes on a characteristic so-called dendritic morphology. Fully solid cast aluminium consists of colonies of dendrites with grain boundaries that have higher energy, leading to potential grain growth. A fully annealed aluminium slab shows uniform grain sizes. Work hardening increases dislocation density, making it harder to deform the material further. At elevated temperatures, dislocation networks form, leading to softening through recovery and eventually through recrystallization, which reduces dislocation density. If the temperature is raised further, new strain-free crystals are nucleated. Recrystallization has commenced, and the material starts to soften. This process continues until the whole of the material has recrystallized and softened. If a fully recrystallized material is held at elevated temperature for a period of time, then the grains grow. Initially, the growth is reasonably uniform, but later, a small number of grains grow preferentially, and abnormal grain growth sets in. In contrast to pure aluminium, aluminium alloys contain solute additions which can markedly affect grain structures, and particularly the microstructures within the grains. This in turn strongly influences the responses of alloys to working and heat treatment. Both crystal structure and microstructure influence mechanical properties. Thank you for watching. Remember to like, comment, and subscribe for more insights on materials science.